Hey, good Wednesday evening, everybody. I am not Scotty Powell. He is off. Today is actually his birthday, so happy birthday, Scotty. Taking a day off to enjoy a little bit of family time. In the meantime, you're stuck with me for the evening and the rest of our cast of characters as well. This is the Wednesday, May 25th, 2016 edition of the Carolina Weather Group podcast and hangout. As usual, we've got a cast of experts in their fields joining us. We've got James and Shay on the podcast this week. Few other folks out and doing some other stuff. We'll give it to James first, just to kind of let everyone know what's going on down towards the Charlotte area. How's everything been down there?
You know, it's heating up a little. It's too bad we don't have Peter on tonight, because I was going to let him take the brunt of complaining about how hot it was up in his neck of the woods. But things have been heating up here a little bit, and I guess the rest of the panelists are all at Scotty's birthday party, and we didn't get the invite. I'm confused about that. But otherwise, it's nice here in the Charlotte area, and without getting dragged into the hype, I hear there could be a shower or two this weekend. I'm just going to leave it at that.
The potential of a Category 5 shower or something like that?
I think so.
I think Shay knows a little bit more about that. Why don't we ask him about what's going on down south?
Well, for right now, we're having some pretty nice weather, some summertime pattern with Atlantic high pressure and some just afternoon southerly sea breezing, pretty modest winds. We are watching an area in the tropics down in the Caribbean, working through the Bahamas right now. And I'll go ahead and share a screen real quick. I don't want to get too much into the weather because we do have a great show on earthquakes tonight. But let me know when you can see this screen.
Yep.
Good to go?
Yep.
Okay, so here's the area that we're looking at, and right now it looks quite disorganized. There's some upper level shear coming up from the south along an upper trough that's feeding down from the Gulf and up across this area. So it's hiding what's going on at the surface, which is right about here. There's a little bit of rotation underneath all of that clouding that you can't see now. We're getting into the nighttime hours, so the satellite's switching to IR feed, but you can barely see it right there in the first frames. And this area is expected to sort of drift up across here and get out of this upper shear environment into a more relaxed upper shear environment. And this is where it becomes more favorable for development. So the National Hurricane Center has just upped this as of 7:40 p.m. tonight to a 30% chance of development in the next 48 hours and 60% chance in the next 5 days. It doesn't necessarily mean that it's going to become a tropical or subtropical system. It just means it's moving into a more favorable area. Some of the models suggest a very weak subtropical or tropical system, and others just suggest it remains as a closed low pressure or a weak low pressure as it hugs in along the South Carolina Georgia coast. I think the biggest rain threat that we're looking at is going to be along the probably North Carolina to Virginia area, maybe South Carolina, North Carolina, and Virginia area. And if the low does hang around in the Georgia vicinity, we could see some additional rains down that way too, probably starting Sunday. Some of the peripheral effects from this may start to arrive on Saturday, but we just don't know for sure yet, and it's still several days out. So we're just kind of keeping an eye on it and watching for development. We won't truly know anything until we get an actual area of closed low pressure.
And Shay, when we look at like the GFS models and the European models now, you know, they're showing excuse me, an area of circulation kind of near the coast. And when we look at the spaghetti models, they're kind of all over the place as you pull up tropical tidbits there. Should we put any emphasis on those now? Is there any use to looking at those products?
Well, it's always good to get some guidance from these models. The GFS and the Euro models are both coming into agreement for this scenario right here, and this is the latest 6 p.m. update. And this just makes it a weak low. I mean, you're looking at 1,015 millibars. It's barely low pressure at all, and it just sort of hangs around in this area, and that's due to high pressure out here building over the Appalachians and just to the west. And then the Euro model also shows this, so you have sort of a suppressing mechanism from winds coming down from the north, and also some drier air along this side, which I don't see this storm becoming anything significant, just because it's not going to be able to acquire a mid-level low and an upper-level low on top. I think it's going to remain more of a surface feature and have some drier and cooler air off of our shelf waters wrapping around from the north and the west. So we'll see what happens with that. I mean, we can take it. You can always look at the Euro and see what they have as well, and that it shows the same situation with the low pressure off the coast of South Carolina by Monday morning. But you see this Appalachian Ridge, and that's going to keep winds kind of coming down in this direction. So this drier, cooler air going out and around the low, and that's why we think that it may take on subtropical characteristics because of this cooler, drier air that gets wrapped into the core, where this low is situated over the cooler shelf waters. Now, if it does stall out here for any length of period of time, or take this sort of track, it's right over the heart of the Gulf Stream waters, and that may allow for more intensification. But right now, we're not seeing any rapid intensification of the storm before it kind of eases over to the southeast coast. So that's pretty much it.
All right. One last question related to all this: would we be dealing with like a rip current risk on the coastline as we go into Memorial Day?
Well, like I said, I think we'll see some of the peripheral effects from this start to arrive Friday and Saturday as the gradient tightens along the coast. We'll probably see some of these easterly winds ahead of it. Let me back this out a little bit. When it gets right about here, we're looking at Saturday, and even into Friday, we start to see the wind field broaden, and you get a little bit of a gradient from this Bermuda high over here, and then the gradient builds between this low pressure and the high pressure to the north, and you get this easterly gradient. So it could be east-southeast, or even east-northeast on some of these localized sea breezing along the coastline, where you get that wind field that comes out. So it could be seeing some moderate winds Friday afternoon and then building through Saturday. I don't see anything past 25 knots at this point. I think that's even a high number. We may be looking at more like 15 to 20 knots on a steepened gradient. But then Sunday, it looks like the gradient relaxes a little bit as that low pressure hugs the coastline. That tends to happen, especially when the storm is not strengthening. And then, yeah, just looking at rain and a little bit of winds through the weekend, and nothing to be overly concerned about right now. But things could change in the next couple of days. We'll have to see because it's moving over some very warm waters right now.
Okay, very good. Well, with that, I'll transition us a little bit from weather into more of our topic of our show tonight, which is hey, look, it's me again. Which is earthquakes. There we go. Shay tries to end his presentation. I'll let you introduce our guest, who happens to have a local connection to your area as well. Can you hear me, Shay?
I think we lost Shay there for a second.
Okay.
My apologies.
Sorry, I was just saying, we'll let you introduce our guest, who has a bit of a local connection to your area.
Sure. Apologies there. This is Dr. Stephen Jaume from the College of Charleston. He's an expert seismologist, and he's here tonight to talk about some of the recent earthquake activity that we've seen in Japan and Ecuador, and what that means for some of the surrounding countries, or even some of the plate tectonics going on around the planet. So I'll hand it right to you, Steve. Tell us about what happened in Japan, firstly, and then move into Ecuador.
Yeah, well, first, I mean, back in, was it April 14th, you had a magnitude 6 earthquake. Not actually right on the plate boundary in Japan, but inland in Kyushu, which is the southern island of Japan. You had a magnitude 6 foreshock that actually did a fair bit of damage, occurring in the middle of a heavily populated area. And I believe less than a day later, a magnitude 7 that did substantially more damage. And earthquakes are not uncommon in Japan. It's on the boundary between actually there it's what's called the Philippine Sea Plate, which is basically diving underneath Japan along what's called a subduction zone. Now these earthquakes did not occur right there at the plate boundary, but further inland within the island of Japan. But they're kind of part of the response of that area to the forces along the plate boundary. Does anybody remember hearing about the 1995 Kobe, Japan earthquake?
I don't personally.
Well, no, I mean, it was one that was pretty significant. Something like more than 6,000 people were killed by a magnitude 7 earthquake that pretty much struck directly within the city of Kobe, which is one of the major ports in southern Honshu, the main island of Japan. And this is kind of one of those same type of earthquakes. It's actually a strike-slip fault, which is, most people will know the San Andreas fault is a strike-slip fault. It's not the main plate boundary in Japan, which actually runs along the coast. So they had that 2011 magnitude 9 earthquake in northern Japan. You may have remembered the one with the big tsunami. That's a plate boundary earthquake. This is actually, for Japan, a minor earthquake. Right? It didn't occur on the main fault, but it occurred where people live. And that's, the thing about earthquakes, when they cause death and damage, death and destruction, it's not so much just how big they are, but where they occur relative to where people live. So despite Japan being a pretty well-prepared place for earthquakes, you put a big earthquake right underneath a populated area, you're going to have a substantial amount of damage. Go ahead.
I said you mentioned how it didn't occur on one of the main faults, but
Right.
all earthquakes are occurring on these fault boundaries, correct? But some of them just maybe not as active as others?
Well, the plate boundary, it's pretty active there in Japan. It's just that the really big earthquakes are rare. Right? No matter where you are, the biggest earthquakes are always the most rare. So magnitude 9 earthquakes occur a few times a century. Right? And that part of Japan that got hit in 2011, I believe the last time that happened was around 896 AD. So over 1,000 years ago. So it gives you an idea. Those really big ones in the same place occur, really usually much more than a human lifetime apart. Equivalent place in the U.S. would be along the coast of Oregon and Washington. The last time an earthquake that size happened there was in the year 1700. In fact, we know approximately what time and what day and what time it occurred, even though there was no European settlement there yet, because the tsunami hit Japan. And the Japanese records recorded the tsunami coming in about what time it was, what date and time, and you can reconstruct, when the source had to be, and they figured it out. It actually did occur on the coast of the U.S., but sent the tsunami all the way over across the Pacific. But
go ahead.
Go ahead. In a sense, a magnitude 7 earthquake is almost run-of-the-mill in Japan, and when they occur offshore, where most of the earthquakes occur, they don't do damage. It's only if it occurs onshore, or actually what are the secondary faults, right under the populated areas, that you see this sort of damage.
2 questions based on what you just said. The first, I'll zero in on the populated areas. What role does media awareness come to whether or not something is considered a big earthquake?
Well, for me or for everybody else?
Well, I guess in your research, I guess there has been a big difference, I would imagine, in what gets...
Well, we use magnitude. Everybody's heard the term magnitude, which is a measure of how much energy is released by the earthquake. So our size scaling is actually independent of whether or not it affects anyone. In fact, because I was living in Australia at the time and working in Australia, the biggest earthquake in 1998 was actually south of Australia on the coast of Antarctica, and no one felt it. It was an 8.3. It turns out I believe the nearest Antarctic research station happened to be unoccupied at that time. Right, so there wasn't anyone close enough. So only penguins felt it. Right. So if you put a really huge earthquake, but if you put it far enough away from people, nothing. Right. You take a much smaller earthquake. In fact, do you remember hearing about an earthquake in Taiwan? I think it was back. Let me look here. I've got it written down. Back in February.
Mm-hmm.
There was this big apartment building that collapsed in it. That was much smaller. It was about a 6.4 than the one that killed far fewer people in Japan. But it happened to be in a place where you had more vulnerable structures, right? So again, it's not just how big it is; it's how big it is relative to where people are and how prepared they are.
And preparedness, I guess, has a big role in that.
Yeah, it's building codes. Enforcement of those building codes. So just because they're on the books, if no one follows them, right, it doesn't matter a lot. If everybody if the rules are breached all the time, they don't really matter, and things like that matter, and details of the physics of that particular earthquake. Actually, how many people remember the one in Nepal last year? A big earthquake underneath Kathmandu.
Wasn't that the one with Everest being involved a lot?
Yeah, Everest was moved by it and everything. They had I guess they had a big avalanche triggered by the earthquake down into the base camp area, if I remember correctly.
Yes, that it's crazy. My brother was there. He did the
oh, really?
He did the hike up to base camp, and that's a long hike. It's treacherous, but he was out there a week before that happened. But there was a couple of people from Charleston that were missing for some time, And
I think I remember that now.
yeah, they had them in the news. But I mean, you know, there's people kind of go there a lot to hike that trail, and yeah, I remember hearing about that. That was pretty scary.
Well, despite the fact that it killed something on the order of 9,000 people, that was actually not a worst-case scenario. It turns out there was actually less building damage than we really expected for an earthquake that size. It turns out there are details in the geology, and the fault moved a little slower, which changes the frequency of the seismic waves, so it didn't interact with the buildings as much as it could have. So that, in a sense, they kind of dodged a bullet. It could have been, in fact, I think the first guesses various people were making. Now, you may not know this. One thing that's done typically these days is when there's a large earthquake in a populated area, there are a number of organizations, including the United States Geological Survey, who try to put out alerts as to potential damage and casualties. They try to make some quick estimates based upon the location, the magnitude, what's known about building vulnerability and population in the area. And most of those, in that case, over-predicted what actually happened. But then there are also always details on the earthquake itself that you can't know ahead of time until the earthquake occurs, that you can't kind of predict on the fly, that also influence whether or not, the degree to which you get different kinds of damage.
Stephen, what's the reason why we always seem to have the earthquake magnitude brought down recently after the initial prediction comes out?
Has it? I guess I haven't.
It seems like sometimes when an earthquake first occurs, we get like a 4.7 rating, and then they'll revise it to like a 4.5 or something. I know in the grand scheme of things, perhaps not as a huge number difference, but in talking earthquakes, the point can make a difference.
Well, sometimes it does go up, actually. Usually the first estimates are rougher, always. You're usually using a smaller amount of data. You're actually using a smaller part of the seismogram, right? The best estimates can really only be made hours afterwards. In a sense, you have to have more data from a greater number of stations, so the waves have to travel across the globe. And you also, with an individual station, have to have enough of that full set of waves to make a better estimate. But I personally have seen it go either direction.
Yeah.
Now, if you're getting a media report, of course, if they hear 3 different numbers, they'll always pick the biggest. Right. So the question is, where are you getting your news? Right. If you're going to somebody like the U.S. Geological Survey, those will move around, but I've seen usually go either direction. If you're relying on a more traditional media source like CNN or somebody like that, they hear there's an earthquake somewhere, they look around, they'll find, what's the biggest number, right? So you got that filter they make. They want to make it a bigger story, right? Get more viewers, et cetera, et cetera. So that that'll happen too. So that may be part of the reason why it seems to go down. If the first reports, the news reports, pick the biggest magnitude they find, estimate, and use that one, it'll almost always go down afterwards.
Is the USGS the recommended source for you? Is that what you would advise people to go to?
That's my first go-to. Basically, they have access to more data than anybody else. So the U.S., let's just say we have friends all over the place, even though it doesn't seem like it. we collaborate pretty much with the rest of the world, including people we don't seem to publicly get along as well with, and a lot of things sort of below the surface. The scientific agencies collaborate, and they typically have more resources than anybody else, right? So whereas they'll share information with everyone else, they kind of have the computers and the tools and the things that a lot of other countries don't. We are a rich country. Gotta remember that. We have resources other people don't have.
Now, Stephen, I wanted to ask you a question. You were talking a little bit earlier about motion. Can you tell our viewers about the waving, the primary waves, secondary waves?
Okay.
Love waves. What are
Yeah.
what are some of the other ones that?
Well, there are two main groups: body waves and surface waves. Body waves, they're called that because where they occur from the earthquake, and they'll travel through the interior of the Earth, and show up at distant locations. P wave just means primary. It's the first one. It's the first one you see. Typically, it's the smallest motion, right? So it's not anything that does damage. I don't know if you've heard about the earthquake early warning systems they have out there. Mainly in Japan, they're actually starting one in the western U.S. now. They rely on the P wave to kind of tell them about where and how big the earthquake is, to try to give a few seconds to a few tens of seconds warnings to different locations before the bigger S wave arrives. So the S wave, which typically has more side-to-side motion, and that's actually what knocks buildings down. It's not up and down. P wave usually has a lot of vertical motion to it. S wave has more horizontal motion, and buildings aren't built to swing sideways. They're built to hold themselves against gravity, right? So up and down motion's in the direction of gravity. If the building's standing, it's already strong in that direction. However, if you kind of take the foundation and shift it sideways several feet very rapidly, there's that inertia with the top of the building that doesn't quite follow. Think about that, right? And the whole building starts rocking back and forth. If the building's not built to withstand that without breaking, then it falls down. So it's that stronger, later S wave that causes most of the damage. Now, there's another, you mentioned love waves. There's another set of waves we call surface waves. This is energy that gets trapped in the upper parts of the Earth and travels around the edges. So it stays at the surface of the Earth. They hold their size out to greater distances. So when you're looking at a seismogram from an earthquake at great distance, the surface waves are largest. But often you're at a far enough distance, they're not large enough to do damage, although they may actually be felt out to significant distances. And those, again, like I said, they're called surface waves simply because there's energy trapped near the surface of the Earth. And so it kind of crawls along the edge, so it takes longer to get there.
How much lead time would a warning system like the ones Japan and the West Coast are trying with give the public?
Seconds to tens of seconds. It depends on distance from the earthquake. So the closer you are, the less warning you can get. In fact, I'd have to go look it up. There's usually within a certain distance, depends on the ability for automatic algorithms to recognize an earthquake has occurred and then locate and determine the magnitude. That will take at least a few seconds to do, right? To get that first rough magnitude and location. So if you're within a distance where the S wave hits you within those first few seconds, you don't get a warning. There's always going to be some distance around the epicenter where you're not going to get a warning just because you're too close, right? So you have to be at and I don't know what this distance is off the top of my head, but if let's say you're 100 kilometers away, it's going to be, let's see, the S minus P time at 100 kilometers is roughly 12 seconds, right, between, in most cases, between when the P wave arrives at your location and the S. If you get a warning when the P wave arrives, you've got about 10 seconds warning. So that gives you a rough idea of what sort of distance ranges. So you'd probably have to be at least tens of miles away from the epicenter to get any sort of warning, right, where it would show up, at least give you a few seconds.
So I learned something, and this might just be my own ignorance with the most recent Japan earthquakes, but it's that earthquakes themselves can almost be indicators and warnings of other earthquakes to come. I was familiar with aftershocks, but as in Japan, they almost had a pre-shock, right, a foreshock.
Right.
What as a society can we do to say, oh, that was a foreshock, we need to prepare for something bigger? Is that a means that we have scientifically?
Yes and no. Yes, in the sense that, in fact, they actually have been doing this for years in California. When they have an earthquake above magnitude 5 anywhere, they say that for the next 72 hours there is an increased chance of an earthquake the same size and larger, and that's pure statistics, right? Looking at the past, saying okay, that there's a chance for every earthquake that it is a foreshock to something bigger. The problem is, the reason why I go to no is that the seismogram of a foreshock does not look any different than the seismogram from another earthquake the same size that's not a foreshock. So there's nothing unique in what we see that tells you it's a foreshock, which is the thing that would say, okay, this one's the foreshock and that one isn't. We just know statistically that when one earthquake occurs, well, basically the physics, when one earthquake occurs, it releases some of the force stored up along the fault, but it also redistributes it. And it may redistribute it on a nearby piece of fault that's itself ready to go, and that becomes kind of, you know, the straw that breaks the camel's back. And if that patch of fault that's ready to go is bigger than the first one, it's a foreshock. However, so you have a big earthquake. Again, it redistributes force around a bunch of faults in the region. A bunch of those are going to pop off in smaller earthquakes. Those are your aftershocks. The physics is the same. It's just that whether the secondary earthquake was bigger or larger than the first one. And that's the only difference between an aftershock and a foreshock. It's actually, there's nothing inherent. The terms are more precise than what we know about what's going to happen, if that makes any sense.
In the moment, they're all earthquakes, right?
In the moment, they're all earthquakes. Yeah, that's a good way of saying it.
And you brought up earlier structures and buildings.
Yes.
And living in Charleston, we've seen a lot of our older buildings that survived, or barely withstood the big one in 1886, the major earthquake. What was that? 8.6 or?
No, it was 1886. It was about a 7.
7. Okay. So we still have a lot of buildings that have truss rods pushed through. What would be your opinion of is the best structure for a building to be able to withstand an earthquake these days?
Oh, I'm sitting in it. I'm sitting in a steel frame, earthquake reinforced new science center on the College of Charleston. It was a requirement, actually, I think, from NASA for the money so NASA gave part of the money to build this building, and it was meant to house all of the NASA and hazards-related programs at the College of Charleston. So that's why I was one of the first people to move into the building, because I'm one of the hazard people. We have South Carolina Space Grant here, but since the hazards folks were supposed to be here, it's like, well, the building can't fall down in an earthquake. It can't be taken out by a hurricane. Part of their stipulation, it has to be built to more than a standard building code. So they deliberately built this one to in fact, we're, if necessary, one of the rooms in this building, our hazard center, is configured as an emergency operations center. So basically, the city or the county, if their facilities are damaged, they could come here and set up shop. Although the new city EOC is on the rebuilt Galliard, the new EOC for the county is actually built to similar standards, right? So all of these local facilities have been upgraded. But we were also built with that idea in mind also. So I was going to ask, what type of materials is it? Is it more of a kind of a flex joint type of building, or is it separated in parts? Is it moved? Okay. Now here's the thing. Unfortunately, I can't take the monitor into another room. But if you ever come here, come to my lab. We actually force the architects to leave some of the structure without a wall to hide it, because they want to hide structural stuff for some reason, architects. We have steel cross bracing with a deformable hinges. So it's bolted on. So basically this formation here, as the building tries to rock sideways, this beam here, the steel beam, goes into compression where it's strongest and it resists that motion. Rocks the other way, the cross beam in the other direction resists the motion. There are hinges on these that are deformable. They're supposed to bend and take and absorb some of the force, right? And then when the earthquake's over, you unbolt them and bolt the new one in place. They're actually disposable. They actually have there are a lot of earthquake engineering, and I know some of the parking garages down here have what they call shear walls in them, which is another. They're actually masonry walls, but they're walls that don't hold up the roof. But they're there if the building starts rocking back and forth, it meets resistance. Now that resistance can be beat to death during the earthquake, As long as it keeps the building from rocking too far back and forth, it works. You don't want to park your car in front of that because then all those bricks will fall on your car, but the garage doesn't come down. So some earthquake engineering actually kind of has disposable elements, right? They're there to absorb the energy of the building moving, and then you take them out and put in new ones later, which is a lot cheaper, obviously, than building a whole new building.
So I'm curious because I had never really thought about that before, where you had disposable parts. But in a
Yes.
scenario where you have multiple earthquakes occurring over the course of several days, is that something where after the first earthquake you got to immediately go in and change out those disposable parts before the next aftershock?
No. Well, what you would do is you would inspect, and if they're severely damaged, you close the building. Or as the sort of rapid response folks do, you put a red sticker on it. Do not enter. Right? They actually, I don't know if people know this. There's a pretty much a standard worldwide. If people are trained to do it, where there's a red, yellow, green sticker system. So a trained engineer who knows what to look for will go and examine a building very quickly, give it an assessment. Green, basically safe to occupy, no significant structural damage, so it's just maybe some cosmetic damage. Yellow is there's some structural damage. Maybe there's things hanging, even some non-structural elements that are about to come loose, right, so that it pose a danger, so it has to be kind of cleaned up and fixed before it can be reoccupied. You might let people in with hard hats to go get their stuff out of their office or their apartment. And then the red sticker is basically we're going to have to tear this one and start down and start over again. So, what happens, ideally what happens, you have people already trained. They survey buildings very quickly, put those stickers up, and so it lets you know you can't go in or can, etc. So if the building does sustain further damage and falls down, hopefully no one's in it in the succeeding earthquakes.
All right, so outside of... Oh, I'm sorry, go ahead.
I said that's the ideal. It doesn't happen everywhere, but that's the ideal.
Gotcha. I was going to ask, outside of buildings, we have roadways, overpasses, and bridges, too, to think about. Cable stay bridges, what do you think?
I don't know enough about them. I know a fair bit about buildings. I've talked with a lot of earthquake engineers and just witnessed myself what happens in buildings. Actually, something, if people are interested in this subject, you might want to look up an earthquake called organization called the Earthquake Engineering Research Institute, EERI. What they do is they have a Learning from Earthquakes program. They send reconnaissance teams. In fact, I think there's the team in both Japan and Ecuador still, or on their way back, where they're making assessments and trying to learn lessons. But they have a lot of different, examples. Have a lot of people who've worked on. Yeah. So latest news. So they have the Nepal Earthquake Reconnaissance Team report. Under latest news is there. The Japan and Ecuador virtual clearinghouses are in existence, so you can go click on those links. And go, and there's also, let's see, looks like there's a webinar available. You can actually look at a webinar from Taiwan, right? So they put out a lot of good stuff. And if you just basically read and try, and then look up terms, right? If you don't know some of the engineering terms as you go along, you can learn a lot about how structures behave in earthquakes and what works and what doesn't. I go there all the time.
It's a neat site. I'll definitely check that out. Going to kind of switch wheels a little bit here, Stephen, because I don't want to burn up too much time. But I wanted to show this map here. I ran this from the USGS, and I'm not sure if you can still see it or not. Did I unshare screen or did I share screen?
You must have unshared it. I can't see it.
Okay, good. I'm glad you said something. Okay. So here's I ran this from February the 1st until present, and this is all the earthquake activity in Japan and around it just since then. So there's an extreme amount of earthquake activity. Tell us the relationship between earthquakes and volcanoes in this area, and the Ring of Fire in particular, and I'm going to show this screen.
Yeah. So you have a lot of earthquakes. Well, can you go back to the earthquake screen?
Absolutely.
If that one shows... I can use that a little more. So you see the red lines on it, right? Those are the plate boundaries. And in particular, now, there's one that kind of cuts through the middle of Japan and goes off to the north. I'd put question marks on that. That one's a little more speculative, right? But the other ones that run offshore, right? Yeah, so that one there is a little bit. Those guys out there, those represent subduction zones. So you see the Pacific Ocean out to the east of Japan, and to the east of that furthest east red line off the coast. The Pacific Ocean crust is diving down underneath Japan and to the south underneath what's called the Philippine Sea Plate, and is basically being recycled into the interior of the Earth. A byproduct of that is you're actually pulling ocean water into the Earth's mantle. That causes, it's actually the water under high pressure, squeezed into the rock under high pressure, causes some of that rock to melt, and then that magma then rises to the surface as volcanoes. So the reason why there's a lot of volcanoes in Japan is that basically you have the Pacific Plate sort of in central and northern Japan, and the Philippine Sea Plate on the southern edge of Japan are diving beneath Japan. So go a little further to the west with your arrow. That one right there, that's where the Philippine Sea Plate is going beneath Japan and Taiwan. So Taiwan...
So this one's moving in that direction. And
that
this one's moving
direction,
in that direction.
exactly. Those diving down are basically the genesis for the volcanoes. So in a sense, both the earthquakes and the volcanoes are due to the same basic mechanism. The diving of these ocean plates beneath the island of Japan, the friction along that boundary generates the forces that produce the earthquakes. The water carried down deeper into the earth by the subducting ocean plate is the genesis for the magma that rises to the surface and forms the volcanoes. Oh, and the water stays with the magma. So think about this for a second. You've got this package of liquid hot rock with dissolved water in it. Underground, of course, it's under a lot of pressure. The water can't escape. What do you think happens what the water wants to do when that magma reaches the surface and gets to the open air? It's got this dissolved water in it.
Probably explodes.
1,000 degrees C, let's say.
I'd say we'd have an explosion.
Yeah.
Right. So that water wants to turn into steam and usually does so violently. So you get, in most cases, very explosive eruptions in places like Japan because of the water in the magma.
I also love the fact, Stephen, that you just, throughout your conversation there, said that the crust gets recycled back into the earth. And if that doesn't make you say science is cool, I don't know what will, all right?
So yes, basically the reason why you have a ring of fire around the Pacific is that Pacific Ocean is surrounded by subduction zones. So you're recycling the Pacific, Philippine Sea, Nazca, Cocos, and there's a couple minor ones like the Juan de Fuca Plate, all being recycled into the interior of the earth. They're in various places, right? And wherever that's happening, you have volcanoes, right? Some cases more, some cases less. You know, there's always details of a particular situation, but yeah, you pretty much, that's where your volcanoes are.
So do you think
particularly explosive volcanoes?
These earthquakes in Japan and Ecuador, do you think that they triggered volcanoes in other areas around the world?
No, we do sometimes see if you have seismic waves from a distant earthquake travel through a volcanic or, say, a geyser region like Yellowstone, you'll see a local uptick in micro-earthquakes after the passage of the seismic waves. So you've got something that's already kind of on the edge of boiling, and then you shake it a little bit. It moves, reacts a little bit to it. There have been a few cases where nearby a large earthquake, if it's in a place like Peru or Ecuador or Japan, you've had a large volcano go off a few days after a large earthquake. But those connections there are still, it hasn't happened often enough for people to really nail what the connection is. Although I'd have to, if you really want to know that subject, friend of mine, Steve McNutt, at the University of South Florida, he's your man. He's a volcano seismologist. So he's kind of the earthquake-volcano connection guy. So that's not a field I know too much about, and I would want to leave it to that expert. for stuff like that.
Steve, I was just looking at a map here, and I think it's an article that you're quoted in, which is how I think I stumbled across it here in Popular Mechanic. But it has a pretty good map that I want to show. If Ricky will send the screen share over my way here as soon as I go and show this, but it actually shows a hotspot, if you will, in your neck of the woods and in a few other parts of the country. I was wondering if you could speak a little bit to, I guess it's the materials in the Earth or the setup, but why is it that a magnitude that might have the same number is felt differently in different places?
Okay. I see where you're going here. Basically, when you in the eastern U.S., so basically Rocky Mountains and to the east, because we have earthquakes less often, and the last time this part of the world was on a plate boundary was a long time ago, the crust is basically much better put together. It's colder, it's more rigid, so when you shake it, that energy can travel much further. So the seismic waves, for the same size earthquake, the seismic waves in an earthquake here in the eastern part of the U.S. are felt out to a greater distance relative when you go west of the Rocky Mountains. You're looking at areas where there's been a lot more recent faulting, there's more recent volcanic activity, it's more beat up, it's warmer crust. That warmer, more beat up crust absorbs the seismic wave energy faster. So the same size earthquake, the waves simply don't reach out as far. Put that together, so when they make a map like this, what they do is you do two things. One, you look at the number of earthquakes occur in different regions. That's how you set up kind of a basic statistical predictive model to look into the future, to say, okay, over a certain time period, how many earthquakes of different sizes do you expect? You put that together with, well, when you have one of those, how far out do the seismic waves of different amplitudes will reach for these earthquakes? And this one here, if it's the more recent version that I'm thinking about, we're probably talking the 1 in 2,500 year earthquake is the maximum sort of standard this is based upon, or a 2% in 50 year probability. And when you do that, and the reason why they do it that way, that tends to capture the largest historic earthquake in each region. So for Charleston, you see the big red angry dot on the East Coast. That's a long enough time period you would expect at least one of the 1886 size earthquakes to occur at that time period. Now you see the even bigger red angry dot in the center of the U.S. That's due to the 1811-1812 New Madrid earthquakes. There are actually 3 earthquakes above magnitude 7 in a 3-month time span, December 1811 and then January and February of 1812. Earthquakes of that size in that region occur sort of like Charleston once every 500 to 1,000 years, so a 2,500 year time span. You'll definitely have another set of those. That's due to that. So, and then there are other earthquakes, more speculative in the southern Appalachians. There's a lot of small earthquakes, but we've not seen a big one there. Similarly, in Oklahoma, while there's been a more recent uptick in earthquake activity that's human-caused, they also have something called the Mears Fault out there, which a few thousand years ago made a pretty big earthquake that we have geologic evidence. So you see that yellow dot in Oklahoma due to that one. And then there are other things up in Canada where they've had some big earthquakes. And again, it's you know you had big earthquakes in these areas. Big earthquakes repeat in the same places over time. That's why you have the big angry red dots in the eastern U.S. Out west, well, then you have, you look at the west coast, you've got the San Andreas Fault. You can pretty much figure out where that is, can't you? Right? You have the other subsidiary faults. You have the big subduction zone along the coast of Oregon and Washington, the U.S. equivalent of what's going on in Japan. That's why you have, Mount St. Helens, Mount Hood, Mount Rainier in Oregon and Washington, the big volcanoes there. There are other faults that run, through around Yellowstone. They run along the Wasatch Mountains in Salt Lake City. They run along the eastern Sierra Nevada mountains. So they run along the edge of California and Nevada. So you can kind of see, I know where a lot of these faults are. I've actually visited most of these places. You're looking at where the big faults are out west, and all the red is along sort of the fastest and most active moving faults in those systems out there.
I have two follow-ups, one being
Okay.
what you touched on with Oklahoma, which I know the other guys are going to want to talk about as well. But real fast, you were talking about some of these historic earthquakes, and I'm not sure if this is just something that needs to be put to rest as a myth, but can a location be overdue for an earthquake?
That's a hard one. I don't know if I would ever put it that way myself. We do know. I mean, you have to accumulate force on a fault before it can have an earthquake. So, and the longer you've been without, as long as you continue to accumulate force, the longer you've been without an earthquake on that fault that releases it, you've got more force on it. So yes, you can to some degree say there's a certain point where there's enough force gathered on this fault now, it's possible for it to have a big earthquake. And I think there was someone in California, I think it was Tom Jordan from Southern California, but at the National Earthquake Conference, I think it was earlier this month, or maybe it was back in April, he said something about the southern San Andreas being locked and loaded and ready to roll. You may have heard that.
Yeah.
It's just been a really long time since you've had an earthquake on that part of the San Andreas, right? So, yeah, it's kind of ready. That doesn't mean it's going to go anytime soon. We don't have a way of telling when it's going to go next, which is what everybody wants to know. We do know that it certainly is in a state where it's accumulated enough force, it can set off a big earthquake. It's loaded. Question is there a trigger out there? And when was that trigger going to be pulled? And that's the part we don't know.
Is there really one big trigger that would trigger the entire event, or do you think it would be segmented? I mean, that's kind of the of the myth. That's kind of the myth that we're led to believe, that there's going to be this big triggering mechanism, and the whole western side's going to crack off into the ocean.
Well, no, that's
Right.
Hollywood, right?
Right.
That part, cracking off and falling into the ocean, is Hollywood. The people who try to look at to see is there something special about the trigger, the first motion on the fault in a big earthquake, is that you can't tell from the first couple seconds, you can't tell big and small ones apart. One of my colleagues who's since retired, Lucy Jones, who worked for the USGS in Pasadena, once had a saying, has a saying which I rather like. The difference between a big earthquake and a small earthquake is a big earthquake is just a small earthquake that didn't know when to stop, is the way she said it. So what she's saying is that just looking at those first few seconds, the seismograph, you can't tell them apart. So there's nothing that she could see in her study that was unique about the big ones. And now to discuss that, we probably need a couple more hours and a few more lessons in nonlinear physics.
Should I go get some coffee?
Yeah, because we really want to get into that discussion, and I would have to do a share screen because I'd have to start throwing equations out. But yeah, then it starts getting, it can get really gnarly to try to figure out why this has occurred. In fact, I'm probably a little rusty on that right now. I'd have to maybe do some study first to remind myself of the right equations to use. But yeah, and that's kind of, for seismology, earthquake seismology, the holy grail is finding that way of predicting when the next big one's going to occur. And I call it the holy grail for a very good reason, because it may be mythological, right? There may be no way of doing this. No matter how much we desire to do it, we may not, the physics may disallow that completely.
That won't stop us from writing movies.
Yeah. Oh, of course not. Well, movies are always fun. Yeah.
Well, I think I was going to ask you about the San Andreas and the media and everything. I think I'll ask that question last about what sort of media we should be looking at. But first, I think that James wanted to talk about Oklahoma and fracking and water injection into the deep earth. So, James, go ahead if you wanted to bring up the Oklahoma topic.
Well, I think Shay set it up there pretty well. And it's one of those headlines and one of those theories that is being passed around, that as an expert in the field, I wanted to ask you about it. And we were just talking about how in Japan water gets inserted into the earth naturally. Does that kind of contribute to what we might be doing ourselves in parts of the country like Oklahoma?
Well, not exactly. We're not putting water in the mantle, so we won't generate any volcanoes. So good news is they don't have to worry about volcanoes. Good news. The bad news is they are pumping water down where there are faults, which are locked and loaded. Bring that turn again. And you've just lubricated something that's already ready to move. So what happens? It moves. One of the things, though, which has been noticed in recent months, is that the rate of earthquakes in Oklahoma has actually started to go back down. What's happened to the price of oil in the past few months?
My credit card statement will tell you it's dropped.
Yes, exactly. So are they selling as much of the oil they're pulling out of the ground now?
No, so am I led to believe they're producing less?
They're producing less, so they're also producing less water byproduct to be disposed of. Combine that with the fact the state of Oklahoma has actually, a while ago now, admitted that, oh yeah, maybe this earthquake uptick is man-made. They've started basically regulating the water disposal industry and saying that, okay, if you're pumping water into the earth in a place that's been having earthquakes, you got to slow down. So they're starting to regulate it. Combine the regulations, combined with the natural slowdown simply because they're selling less oil, therefore pulling, since the water is mixed with the oil, they're pulling out of the ground, right? They have less water to dispose of in the first place. You're pumping less water in the earth, you're getting fewer earthquakes.
So, Stephen, what
correlation?
You're living in this area. You're living in Oklahoma. You're a resident, and there's an acceptable amount of earthquakes that you're willing to deal with for the type of energy that you're trying to get out of the ground there. At some point, it seems like it would be believable that they are man-made earthquakes. And is there any legislators trying to fight it? Or is there anyone that's deeply concerned about the safety for the citizens of the state of Oklahoma?
There are. Well, the state of Oklahoma actually has. Again, they've admitted this is occurring, and like I said, they're actually actively regulating it now. It took a few years before they got to that point. There were actually quite a lot of people, because the petroleum industry is one of the linchpins of the economy in Oklahoma. So there was a lot of, how should I say, pressure not to do anything for many years, but eventually it became too much. And too many other scientists not working for the state of Oklahoma. Now, I actually know at the time, the person who was the chief state seismologist for Oklahoma, he actually quit a little over a year ago and went and worked for the U.S. Geological Survey because I think he wanted to not die of stress. Because believe me, he was in a very stressful situation. In that what he was saying behind the scenes to his state legislatures and the governor's office and everything, and what he was allowed to say publicly for a few years there were not the same thing. I know this for a fact. Pretty much anyone who's spoken to him, he'll tell you the story. But it took a while before they admitted to it and began doing something about it. But it does seem to be paying off. There does seem to be a reduction in. Now it's still far higher than it was 10 years ago, right? But there has been a reduction in the rate of earthquakes, so they seem to be starting to get a handle on it.
Do you think that the area is less prone to feature large quakes, or do you think that they've released some of the? In other words, I guess what I'm asking you is, do you think it's put them in a more dangerous situation than ever now, or did they release some of the pressure that was already there?
No, they're in a more dangerous situation now. The problem is we don't know enough to say exactly how much increased danger it is. When you have you've in a sense you've upset the pre-existing equilibrium of the fault system, and you've put it into a new state that has a large human. Even if you stop pumping right now, it will take probably years to decades to have the anomaly work its way out the system. And during that entire time period, you're not back to normal. So the possibility of a large earthquake, a larger, more damaging earthquake, is high now, and will stay high until higher than it was before, until things get back to normal, which could easily be decades at this point. It's going to be a while. They're in a more dangerous situation for a while. They've already done too much for things before things will get back to normal.
Now, is this a problem in Oklahoma because of the way the ground is there versus, say, where the drilling operations are in Texas?
Well, they're having the same issue in Texas, just not as dramatically. They're actually are having the same issues in Texas. Probably they simply, well, the geology in Texas is different, so they where they dispose of these waste fluids is at a different level. So not as much of it goes deeper into the crust into what's called the basement rock. The stress on the faults are different in the basement rock in Texas, and I don't know enough about the difference to speak intelligently about that. But they're different geologic regimes, so they're going to be different to some degree. And the combination is going to lead to differences. Actually, if you look at where the earthquakes are in Oklahoma, most of them are north of Oklahoma City. They also pump fluids into the ground south of Oklahoma City, but the Earth's crustal conditions are just not conducive to basically setting off fluid-induced earthquakes.
Shay, I know we're coming up on 9 o'clock. I think you might have one or two more questions before we really begin to wrap things up here.
Yes, sir. I did want to ask you something. We look at, as meteorologists, we look at the National Data Buoy Center arrays out in the ocean. Is this something that you use regularly, especially for tsunami watch? Because I know that the Pacific array is here, and then we have a little bit of an Atlantic array. Do you feel like the eastern United States is covered well enough, or are there areas of the planet that we should have better coverage for?
Okay, find the DART buoys. You see on your left, go up near the top, all the way to the left, you see DART, D-A-R-T. So pull your cursor over to the left menu bar, all the way left.
Okay, gotcha.
Go up so you get to DART. Up, 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 stop, hit those. Those are the tsunami buoys.
Okay.
Those are the ones specifically. DART stands for Deep Ocean Assessment and Reporting of Tsunamis. And yes, if I know there's been a big earthquake in the ocean and there's a tsunami, I usually go check those out and watch the tsunami go by.
Okay, that's good information to know.
Yeah.
Now that's far less buoys than we were seeing a second ago. So do we need more of those type buoys?
For the United States, we're probably good. They're in the right places. So like there's the one off 375 nautical miles due east of Charleston. That's our local, so it's meant to catch something either coming across the Atlantic or up from the Caribbean on its way here. Of course, you have the ones north of Puerto Rico, which will catch it first if it's coming up from the Caribbean. Now, the Europeans have not quite gotten their act together. They're supposed to be deploying things off the coast of Europe and North Africa and in the Mediterranean, but as you see, they're not there yet.
Right. Yeah, I see that. Looks like the ring of fire is all covered. This one, I think, was in the news not too long ago. I think that they just forgot to update the settings on it, and it sent a water column, I think, 60 meters in height or something, and it got people a little bit rattled. It was a false reading, but it got people a little bit rattled because they thought, oh man, should we?
Something bad's like, yeah. That would...
So.
How much lead time would that give the East Coast?
Well, at that point, not much. If it's already reached there, depending on where it's coming from. Now, what would happen is, to generate a big tsunami on the East Coast, you'd have to have something like the magnitude 9 Lisbon, Portugal earthquake happen again off the coast of southern Europe, or maybe a big volcanic eruption in somewhere like the Canary Islands have a big chunk of island fall off into the ocean. But you kind of know those have already happened, so you'd be looking. And there are other sensors out there. They can use some of these other buoys. I mean, I don't know specifically how those sensors are configured, but I'm sure they could interrogate some of those guys to help them out also. You probably know more about that than I do. And also, the tsunami would hit the coast of Africa and Europe first, so we know there's one out there. And you'd have a rough idea when it would arrive. So we'd have hours of warning. Something like that is not going to, particularly these days, is not going to go unnoticed. We'll know it's on the way well before it gets here. And then when you see me leaving rapidly, driving away, you'll know to follow, Shay.
I'll keep up with you. Just send me a PM or a tweet if you would. Last question for me for the night. And we see a lot of media sources out there. We have Washington Post. We got sources from England, sources from all around. When we see news articles coming around in the media, what should we believe? What should we be looking for as key phrases or things to be concerned about in the articles, true value or worth, and where should we be looking for actual real sources and good material?
Well, let's see. Well, thing is, often they'll get, question is, where do they get their sources? I haven't really thought about that one that much. I don't tend to scan these news articles and specifically try to figure out where they're getting information. Sometimes they will say, if it's an article, if they have a name, obviously, in an organization, you can go find that person and figure out whether or not they're likely to be someone reputable. A lot of times there's some new scientific study come out, so the press office at a university or at a research lab will put something out and this gets picked up by the various news organizations. I'd usually try to get back to try to find out who the originator is, and what that paper or study actually says versus what the press release says, because the press releases are always sensationalized. And when you kind of read the details, you start realizing, oh, okay, it's not quite what the scientists are saying. It's not quite what's in the media, and it's kind of a sad thing. I think part of the problem is if you don't sensationalize it somehow, it gets ignored, even if it's important, right? But on the other hand, you can't rely on the sound bites to tell you truth. Of course, you've probably seen enough, particularly these days. If you pay any attention, you may notice there's a presidential election this year, and you've seen things in the news that different people say, and if you go look a little more closely, you get the full context of what's happening, and it might be a bit different than what's in the headlines. Same thing with most science stories. Right? You got to be a little skeptical. If it sounds a little too outlandish to be true, it probably is. Does that make any sense?
Sure. Yeah, I'll just come to you from now on.
I'm just kind of winging it off the top of my head to answer that question.
Sure.
So last question of the night is one we tend to end on.
All right.
We get a lot of people on this show who forecast very traditional weather, so I'll be very interested to see the answer to this question, because this is a very unique and a very interesting topic that will fit into this question nicely. But if there is somebody listening to the show, a teacher or a student, who are looking to get into this field, what advice would you have for them on something they could get started on right now?
They get started on right now.
To expand their knowledge base.
Okay, I would go to a group called the Incorporated Research Institutions for Seismology and find their educational materials. So Iris, let's see, I'll get my link up to them. They're one of my links. And yes, it's an organization. Let's see. Okay, there's the. It's one that in fact, the first thing when I came to the College of Charleston is I made sure the College of Charleston joined. It's a university-based consortium. While it's research universities, they have a very significant education and public outreach arm, which I was actually on their outside standing committee until the end of last year. They have a rotating committee of people who give them advice. And I'm actually leading a special interest discussion at their every 2 year, whatever that's called, annual workshop. That's why I'm going to Portland next month. I'm leading one of the discussions on teaching undergraduate seismology. So I'm kind of on the education end of that organization, and that's a good place to start. I mean, they have a little bit of everything. Right, they do. Whenever there's a newsworthy earthquake, They have what they call their teachable moments, a slide set they put out there, so any teacher can pick those up right away. They have lots of videos and animations. There's different levels of software for different kind of novice through intermediate and even expert level software to explore seismic waves and explore earthquakes. Right? They've got a lot of different things, and they're always working to expand their holdings. So it's a good resource. And they have links to everybody else, of course.
Those teachable moments, those slides sound extremely helpful.
Yeah. So I see. What's the latest teachable moment? Recent earthquake teachable moment. The latest one. There was one. Did you know there was a magnitude 7 earthquake underneath Vanuatu on April 28th?
Not off the top of my head, no.
No, because that one didn't really make the news. But the next one after that was the 7.8 in Ecuador that knocked a bunch of buildings down, and that one made the news. Right, and they have one there for that one also. And there's a whole list of them going back years.
That sounds like a great resource for both students and teachers to hop on and get started. Is there any place where people can reach out to you, maybe on social media, and follow some of your work?
I'm not big on a social media presence sort of person. Not professionally, at least. I mean, I've got a personal Facebook page, but not a professional one. For the College of Charleston, we do have a group called the South Carolina Earthquake Education and Preparedness Program, SCEEP, SCEEP. And we've got a website, so we have our kind of local resources, education resources you can get through that website there. So if you look up SCEEP, I should be typically the first. Yep, scearthquakes.cofc.edu. So that's us. Right, and so you've got my colleague Erin on the first panel, Norm on the second, and I'm on the third. Where it says for the press. Yeah. So I just had a quick look at it. I forget who's first, second, third. I don't remember. I don't go there much myself.
They're not ordered any particular fashion. You guys didn't draw straws. No.
We like hired a student who knows how to make web pages to put it together for us. And I think Norm, my colleague Norm Levine, was the person who kind of oversaw that. He's more the hardcore computer guy here. But we do have an Ask a Seismologist thing where you can submit a question and one of us will pick it up. Right. So we do have those sort of things, but we don't have the resources that IRIS or the U.S. Geological Survey or somebody like that has. So we're pretty small scale here.
Ask a seismologist. I like that, though. I will keep that in mind.
I think the USGS has a similar thing somewhere, too. I think if you go to their earthquakes page, there's a button to ask a seismologist there also. I know Caltech, I'm pretty sure, has one. Different places actually have something similar.
Do you guys have your own seismograph?
No, we don't, but it kind of don't need to have your own anymore. Everything's on the internet.
Yeah.
And if you have the right software and know how to use it, you can download stuff from several thousand online seismometers at any moment. And I do mean thousands. I do mean thousands.
Where are our readings in the Southeast taken from?
Well, there's ones all over the place.
They're all over the place?
There are probably about a dozen in South Carolina. Going at any one time, or probably more than that now. There's a pretty good since the earthquake in Virginia back in 2011, and by the way, also the tsunami-generating earthquake in Japan that destroyed a nuclear power station. Right? There's been a concerted effort to keep closer look at the U.S. because I don't know if you remember the Virginia earthquake actually damaged a nuclear power station slightly, but it actually caused a shutdown of a nuclear power station in central Virginia back in 2011. So
we have a new one coming up in South Carolina now. So
yeah. So I know all about those guys.
Shay, yet another reason that if you see Steve running,
The thing is, I won't be running inland in that case. I'll be running towards Georgia or towards North Carolina. I'll be running parallel to the coast instead of perpendicular to it. So if you see me running parallel to the coast, there's a nuclear meltdown inland. See me running away from the coast, there's a tsunami coming. So let you interpret that.
GPS fun, instead of fun will all to be fun, Steve, and I'll be following you. As soon as I see you head inland, I'm right there.
Alrighty, I think we're good for tonight.
Alrighty, well, thank you. That was fun.
Yeah, we appreciate you coming on and joining us for a little bit to kind of switch aside from our typical weather topic and get all the sciences involved. So.
Yeah. No, I do pay attention to. I've seen some of the things Shay was showing about the tropical tidbits was one I had not known about. I know of other websites where you can see some of the projection, the models that will project these lows forming and deepening as they come up the coast to form these tropical systems. So I'm glad to know of a new one now. I follow that stuff too. I mean, it's still physics. I'm a geophysicist. This is, it's fluid dynamics instead of seismic waves, right? Since both the atmosphere and the ocean are fluids, right? But it's, still kind of the same general branch of dynamic models and physics that seismologists use, or people who do climate studies use, right? It's
all the science.
Every once in a while, we cross paths when we get our sonic booms off the coastline during an atmospheric inversion, and we get compression waving and some things that will affect your instrumentation. That then becomes a part, kind of both of us involved with that. So we've had a couple of those this year, and some unsettled people. Whoa, what was that? Was that an earthquake? And then there was one actually not too long ago that was just thunder. It really was just thunder. It was from very far offshore, the very, very light southeast wind, which is directly on shore. And the lighter the wind you get, the better the sound travels, and it actually amplifies into the coastline. So it wasn't a sonic boom, and these storms were probably 30 to 40 miles out. They were just sounding off really loudly along the coast, and there were several of them. And so, yeah, every once in a while we get, we cross into each other's territory, and it's good. It's good to touch base with you every so often on those.
All right. Okay.
All right.
Guess that's it.
Yeah, we will wrap this up. This was the May 25th edition of the Carolina Weather Group. We thank everybody for joining us tonight. I do not know our topics for the next couple of weeks because I'm not Scotty, and Scotty usually takes care of that. So we have another show Wednesday, I promise, but I'm not sure the topic. But Scotty will be back next week and be able to round this all together and do a lot better job than I just did. So hope you have
Scotty's the kid on the group project that does all the work.
Yeah, pretty much. But hope you have a great Wednesday. Have a great Memorial Day. Stay safe. Be aware of those rip currents at the beach, and hopefully it doesn't rain on if you have any beach plans as well.
All right.